Hello, men and women of science. This is Mr. Cochran here to talk about scientific notation and powers of 10. Why scientific notation in science? Well, in science we use very large and very small numbers, and those numbers can have a lot of zeros in them and a lot of decimal places. And so scientific notation helps us write those numbers more efficiently and more quickly. For example, if I had to measure the diameter of an atom, that would be an extremely small number. If I had to count the number of atoms in a grain of sugar, that's an extremely large number, and we represent those numbers in scientific notation to make them easier to work with. It's also easier to perform calculations when numbers are in scientific notation when they're really large and really small. And we can also use scientific notation to show the correct number of significant figures in really large numbers. So here we go. Let's talk about some powers of 10. Here's some powers of 10, 0 through 5, and 10 to the 23. You'll notice 10 to the 0 is equal to 1. In fact, any number raised to the 0 power is equal to 1. You see 10 to the 23 is this really large number, and I'm guessing you'll notice a pattern here that 10 to the 1 is 1 followed by 1 0, 10 to the 2 is 1 followed by 2 zeros, etc. So 10 to the 23, if you counted these out, there would be 23 zeros there. The number of atoms in a mole of atoms is 6 times 10 to the 23rd, and that's the significance of that number there. And so it would be much easier to write 10 to the 23 than to sit and write out all these zeros, or even if I was reading this to try and count those zeros. So there's one of the advantages of using exponents in science. And so let's go over some powers of 10 and convert some numbers raised to a power of 10 to what we call standard form. And so 2 times 10 to the 1, you know that 10 to the 1 is the same as 10. So 2 times 10 to the 1 would be 20. So starting out really simple, how are we going to convert 2 times 10 to the 1? Well, you write the number 2, you scoot the decimal 1 to the right, and you add a 0 to fill in the blank, and there you go. 2 times 10 to the 1 is 20. 2 times 10 to the 3 would be done in a similar way. We're going to multiply 2 times 10 3 times, and so put the number 2 there. Every time I multiply by 10, the decimal scoots 1 to the right, and so we do that 3 times, and we add 3 zeros, and 2 times 10 to the 3rd is 2,000. So using powers of 10 is a pretty simple operation. When you have positive powers of 10, you're going to move the decimal to the right once for every power of 10. So 2 times 10 to the 6th is 2 million, or 2, with the decimal scooted to the right 6 places. So 0.0057 times 10 to the 6th, well, we're going to move the decimal to the right 6 places from where it was to its new location, and that would be 5,700. So every power of 10 is 1 decimal place. Positive powers of 10, it's going to get 1 decimal place bigger. But what if we're working with negative exponents? Well, negative exponents really mean 1 over that number raised to the exponent. So 10 to the negative 1 is 1 over 10 to the 1. 10 to the negative 2 is 1 over 10 to the 2. This would be 1/10, or 0.1, 1/100. 10 to the negative 3 is 1/1000th. 10 to the negative 5 is 1/100,000th, and I don't know if there's really a name for that, but that's a really small number. 3 times 10 to the negative 1. Well, 3 times 10 to the negative 1, as you saw in the previous slide, 10 to the negative 1 is 1 over 10 to the 1, or 1/10. So 3 times that would be 3 over 10 to the 1, or 3 divided by 10 one time. When you divide by 10, multiplying by 10 with a negative exponent, you're going to move the decimal 1 place to the left for each power of 10. So I have a 3, I'm going to move the decimal 1 place to the left, and so 3 times 10 to the negative 1 is 0.3. Notice we put a 0 here in science. When we have numbers that are less than 1 written in standard form, we always start out with that 0 first. It lets us know where that decimal actually is. And so 5 times 10 to the negative 2, just like before, that would be the same as 5 times 1 over 10 to the negative 2. 10 to the negative 2 is 1 over 10 to the 2. So 5 times 1 is 5 over 10 to the 2. We're going to divide 5 by 10 2 times. So we're going to scoot the decimal over 1 2 places, and that equals 0.05 or 0.05 or 5 hundredths. Okay, so 0.017 times 10 to the negative 3, we're going to divide this number by 10 3 times. That's going to make it even smaller than it already is, so we're going to move that over 1, 2, 3 places. We're going to fill in the blanks with 0, put the decimal in its new spot, and there we go. How about, and then one more here, 4.52 times 10 to the negative 5. We're going to scoot that decimal over from its location 5 times, and our final answer then looks like that. So to write a number in scientific notation, we want one non-zero number to the left of the decimal, and it needs to be raised to a power of 10. So we're going to go through this and learn how to do that very quickly here. An example of a number in scientific notation is 4.61 times 10 to the 12. Another example, 1.04 times 10 to the negative 5. Notice that this is a number with one non-zero to the left, or a number between 1 and 10, and it's raised to some power of 10. So these numbers are both written in scientific notation. These numbers, however, are not written in scientific notation. Can you see why? Let's look at this first one. In this first one, there's two numbers to the left of the decimal, not one non-zero number to the left of the decimal. In this next one, we don't have a non-zero to the left of the decimal, and then in this last one, it's just not raised to a power of 10. So these three numbers here are not written in scientific notation. So how do we convert from standard form to scientific notation? Well, you're going to shift the decimal so that there's one non-zero to the left, and then you're going to raise it to the appropriate power of 10. And we just looked at how to do that in the earlier slide. So let's take the number 50,400 and write it in scientific notation. And we're going to shift the decimal so that there's one non-zero to the left. We're going to raise it to the proper power of 10. So if you write the number 50,400, the decimal normally would be there, but we need to move it over 4 places to get one non-zero, in this case the 5, to the left of the decimal. So since we moved it 4 places, this would be 5.04 times 10 to the 4. So this number and this number are equal. 50,400 and 5.04 times 10 to the 4 are equal values. This one is written in scientific notation, and this one is written in standard notation. This number, as you can see, is pretty small. It's way less than 1. And so we're going to shift the decimal so there's one non-zero to the left, and we're going to raise it to the appropriate power of 10. This time we're going to have to shift the decimal down 1, 2, 3, 4, 5 places to get the 9 one place to the left of the decimal. We want an equal value. This is a small number, so we would have to divide 9 by 10 5 times to get 0.000090. We include this 0 here, and we'll be talking about that when we talk about significant figures, but this 0, 9.0, would be included in this value. When you have these small numbers and you're shifting to the right, you're going to include anything else that follows to the right. And we'll talk about that more when we talk about significant figures. Let's look at another example. Let's write this number in scientific notation. You'll notice that we don't have a non-zero to the left of the decimal, so we're going to have to shift it down 3 places. And since this is a small number, again, we're going to have a negative exponent. It's a number less than 1. We moved it 3 places, so we have 7.00 times 10 to the negative 3. Move the decimal down 3 places. 7 divided by 10 3 times would equal 0.007. We have these 2 zeros there, again, because they're significant values, so we'll look at that more later on. This number in scientific notation, as you can see, the decimal would normally be right here. We need to shift it over 4 places, so this value is 6.0901 times 10 to the 4. Multiplying this number times 10 4 times would give us this same number that we have right there. So converting between numbers in scientific notation and standard form and back is really not difficult at all. So 800,000, and it says to write it to 3 sig figs, and again, I forgot to edit that out. We're not going to worry about sig figs right now, but we're going to move this decimal over 4 places, 1, 2, 3, 4, 5 places, and that's going to be 8 times 10 to the 5. And that is not written to 3 sig figs, but I'm not going to remake this video, so just ignore the 3 sig figs part. All right. And so can you write this number in scientific notation? Let's give it a run. Here we go. We're going to scoot the decimal down 1, 2, 3, 4 places. This is a number that's less than 1. Remember, that means that we're going to have a negative exponent, and we shifted the decimal 4 places. So 2.9 times 10 to the negative 4 is the same as 0.00029. Okay, so now it's time for you to try some of this. Go ahead and pause the video right here. Jot this table down. We have numbers in both standard form and in scientific notation. See if you can convert these numbers to scientific notation, and see if you can convert these numbers in scientific notation back to standard form. When you restart the video here in a second, I'll go ahead and play the answer slide. So hit pause now. All right, so here's the correct answers for these. Numbers written in red are the answers to the blanks that you had there on your table. So I hope you're getting this. If you don't, you might want to watch this again. But it's really simple. It's shifting decimals left, right when we're working with powers of 10. Thanks. Bye.